Okay, Assalamu alaikum, shabab. Welcome back to the class. Before I get started, ya akhwan, there was a student who told me in the other class that I think he's Faisal. He did it twice, sent me the result of a survey to delay the quiz. And he said that mathematics, I think Math 333, has announced that there will be an exam this Thursday. And he told me if it is possible to delay the quiz to Sunday. I told him if he can run the survey again between all of you, and the majority said, okay, I will delay the quiz, okay? So you should, I think, hear from him, and I should hear from you back very soon before we decide the quiz, okay? All right, ya shabab. If you recall, let's get started with the lecture. Of course, today, what are we going to do? We are going to discuss the static problem. And because ultimately, ya shabab, we want to deal with bolted joint under static loading and under cyclic loading. So today we are going to solve one problem about static loading. And we will start talking about the fatigue loading. And then when we finish fatigue, by maybe next class, we will talk about shear joint. Okay, joint which are bolted, but they are subjected to shear loading. Because everything here with respect to static and fatigue is related to tension joint, okay? And then we will talk about shear joint. Good, ya shabab. So if you recall, last class we talked about the last slide was we discussed the preload, and we said that preload Fi is calculated based on the type of joint or connection. Is it permanent or non-permanent? And we said that it is 75% of the proof load and 90% of the proof load for both non-permanent and permanent, respectively. Okay. We said, how do we find FP? It is very simple. It is tabulated value. It is the multiplication of this SP multiplied by 80. In the case, if you don't know what is SP, then you can multiply the yield strength of the material from which you made the bolt. You can multiply it by 85%. And then you multiply it by the tensile stress area. Now, the tensile stress area, shabab, you should be able to find it, because even if it is not tabulated, you think that you will cut the thread based on ASTM standard or SAE standard, and these standards list the tensile stress area for a certain type of cut. So you should be able to match it with it, okay? Now, what are we going to do next is we are going to talk about, this problem. I'm going to show you the figure later. But in this problem, it says that we have a pressure vessel, kind of, and it is bolted. And the vessel itself is made of cast iron, 25 cast iron. Grade 25, you go and see it, I think, in table A24. And we want to know what is the total number of bolts required to be used to resist a separating force of 6 kilo-pound, 36 kilo-pound. So we will determine KB, KM, C, and then we will determine the number of bolts based on the assumption that the load factor is equal to 2. And after that, we will determine what is, after knowing what is the actual number of bolts, we want to find the load factor again, the actual one, because it is going to be affected by the number of bolts, and then the yielding factor, which is related to proof strength, and the joint separation factor, N0, okay? Now, as for the joint itself, this is it. So let me zoom in again over here. So need to fix this right. Come on. So what do you see here? You see a cast iron, yeah, shabab. And this is a sealing. If you look, this is a seal. And what we have here is 5-8 inches. That's the diameter. Then we have 11. That's N, the capital N, the number of a thread per inch. I don't blame you, Shabab, if you get confused. I mean, this book was written by Shigley. Long time ago, he died. And it was probably the best book available for classes and teaching. People now revising this book, and each time they do something, they make it worse. Now, I would assume that a good revision would say that N, the number of bolts, number of thread per inch, should be written in NP something or something. But it is the same N as the fatigue life. It is the same N as what is the number of bolts. So please don't be confused. Okay? Don't be confused. This is UNC, which is the coarse threading, and then 2/4 of an inch, the total length of the bolt, and then we have a grade 5, okay, and we have a hexagonal nut as well. The grip, you know, the cast is 3/4 and 3/4, 2 plates, same thickness. So the total here is 1.5 inches. Okay, and says here in the drawing, this is number 25 cast iron. Just to know, if you are interested to know the ultimate, the strength, and so on of the material. Now, we are going to solve this problem. I'm not going to try to solve it in every single detail, but just to give you the feel, okay, of it. So what are we going to do? In the beginning, ya shabab, we are going to say, okay, the length of the grip is 1.5. I just told you that. It is 3/4 plus 3/4. We go to table A31, and from table A31, we will find that the hexagonal nut should have a height of how much? 35/64 inches. And then if we just, in the solution, it is just showing you that the total length of the bolt, which we know it was given to us, it was 2.25 of an inch, 2.25 of an inch. If we want to know how to estimate it, basically, we need first to add the height of the hexagonal nut, which is 35/64. So this is 35/64, plus the bolt should at least have the same height as the grip. The grip was given to us as 0.75. So this is 1.5. Then plus we add 2 threads. Now, the 2 threads, we said that 11 is the number of thread per inch. So 11 is thread per inch. So if you take the reciprocal of that, you will have 1/11, which is inch per thread. Now, if you multiply this by 2, which is 2 thread, 2 thread will go with 2 threads as a unit, and you will left with 2/11 as a length of the 2 threads. Okay? And with that, you will end up having the entire length of the bolt. So the total length here is going to be 2.229 inches. And then if you go to table A17, get the standard next length, it will be 2 and 1/4, which is what we have been given in the problem. Okay? This is just to show you how the book here is showing you the calculation. Or تدرون يا شباب, maybe, I don't know, maybe the book did not, the questions was confusing. Maybe the bolt specification were not given to us and we need to find it. But at that case, nobody told us to use a grade 5. So just take it as is. In the exam, you should be given all the information. Okay. Now, if we now know the length of the bolt, then LT, if you remember, LT is 2 the diameter plus 1/4 if the diameter is less than 6 inches, which is the case here. I mean, 5/8 is less than 6 inches. So what are we going to do? We will find LT, which is equal to 2 multiply 5/8 is 0.625, and then plus 0.25, and this is going to give you a number. The length of the thread is 1.5 inches. Then what do? We need to find LD. Why are we doing this? Because we need to find KB. We need all of these numbers. LD is going to be equal to the length of the bolt, which is 2.25, minus the length of the threaded portion, which is 1.5, and we will get 0.75. And then we will have the length of the threaded portion within the grip equals to the length of the grip minus LD, which is going to be 0.75. Okay? So when we calculate these numbers, we need to go now to the table and find AT. AT from table A2, you will find it to be 0.226 inches square. And AD, which is equal to pi/4, and the diameter is 5/8. So it is 0.625 square. So when you find all of these, you can find KB, which is equal to AD multiplied by ATE divided by AD multiplied by LT plus AT multiplied by LD. And when you calculate all of this, you will get 5.21 megapound force per inch. This is not very clear, so let's clean it up. Now, what do? We go to the grip. The entire grip is made up of cast iron. So since it is made of from cast iron, then we would say that Km is equal to 0.577 4 by ED divided by 2 len, and then 5 multiplied by 0.577 4L plus 0.5D divided by 0.5774L plus 2.5D. And if you calculate all of this, you will get 8.95 megapound force per inch. Good, ya shabab. Do you have any question? Of course, all of this, something we covered before we talk about the bolt strength. So in a question, you are either given these values, or if the question wants to examine you in everything, you will have to calculate them like now. Now, if you do this, the most important now parameter to do the static analysis is C, which is KB divided by KB plus Km. And this is going to be equals to 5.21 divided by 5.21 plus 8.95. And this is going to be equal to 0.368. Good. Now, the first thing we were asked to do is to calculate the number of bolts. Now, NL, which is the load factor, is equal to SP AT minus Fi divided by C multiplied by P, C multiplied by P. Now, what is P here? P is the number of the load per bolt. So what do we have is this. Sorry, ya shabab. Let me clean this up. So P is actually equal to P total divided by N. How much is the total load? And how many bolts do I have? And then each bolt will take a little portion of that total load. So in here, I know N, L, it was given to me. It says assume it to be 2. So this one is given to me. What is AT? I calculated, I obtained the T from the table. I didn't calculate it. Now, what is SP? We know that this is a grade 5. And by knowing that this is a grade 5, and by knowing that this is a diameter of 5/8 inches, knowing these values will tell me what is the proof strength, which turns out to be 85 kbsi. Okay, now what is Fi? Fi, in the question, I forget to tell you, if you go back to the question, what does it say? Let me go back so I can show you this keyword. It says, find the number of bolts required for a load factor of 2 where bolts may be reused. That word reused means it is not permanent. You want to reuse them again. So this is going to be 0.75 multiplied by SP, which is 85, multiplied by 80, which is obtained from the table. Now, C, we just calculated it to be 0.363, was it? 0.363. B total was 36 kilopound. So the unknown, the only unknown is N. Now, if you calculate N, you will find it to be how much? It is going to be C N L B total divided by SP80 minus Fi. And if you substitute the values, you will get this as 5.52. Now, how many bolts do I need? How many, Shabab?
6.
I need 6. Why? I mean, if I need 5.2, I cannot put 5.5. I cannot put half a bolt. And if I can't, I need to, round up, not round down. So I will use N as 6. Do you understand? Now, when I use N as 6, I can go and calculate NL, which is equals to SP AT minus Fi divided by C multiplied by P total divided by N, which is going to give me 2.18. By substituting this as 36 and this one as 6, the remaining variables are still the same. So now what happened is I go and let me continue. I go then and then find NP. Now NP is equals to SP AT divided by C multiplied by B total divided by N plus Fi. I know everything in here. So when I substitute, I get 1.16, which is not too far higher than 1. And this is something we told you about. We told you that the proof factor, this yield factor, which is based on proof strength, will not give you a far limit from 1 because the load is, gonna push the stress in the bolt near the proof strength. The last one is N0, which is for separation of the joint, which is Fi divided by P total divided by N multiplied by 1 minus C. And if you calculate this, you will get it as 3.8. which means you are really good. You're safe with respect to the separation of the joint. Okay. Now, if we go, this is the solution. Okay. You can go over it yourself. And here, ya shabab, this is a problem which I want to discuss a little bit. This is a metric problem. Okay. And also, it's a very common problem. You know, it can come in the exam, in the homework. So why I want to talk a little bit about this problem? Because what happened, ya shabab, is this. If you look that this is the pipe, okay? The pipe is like this. And the brusher, let's assume that the fluid is here running. But as the fluid see this gap, it will go inside in yellow. Now, this brusher, ya shabab, this brusher P, if you multiply it by area, P by area, it will give you a force. This force is going to be applied on this. And then if you imagine that there are two bolts, this force is going to be distributed on the bolt. So logically, ya shabab, what you need to do is to multiply the brusher, which is not difficult. In the industry, ya shabab, you know that they put a gauge, and the gauge will measure the brusher for you in probably BSI or kilopascal, something like that. So when you read the brusher, you may ask them about this diameter, but you need to be very, very careful. Why? Because an area, you may think that this is the area over here. It's a round area. But this is the ceiling over here. ويا شباب لما نحط السيلينج خلاص احنا نعرف بأنه the ceiling is there because it prevents leakage. And if it is a little bit far, it means that reasonably the fluid is going to go here and it will go here. So what is the area right now? Now here, maybe if I represent the brusher like this, okay, maybe here you will have only a little area, okay, and it is not very different from, it's not too big, but it is still an area. So what happened? You need to be very, very, very careful. Very careful. Why? Because in the solution of this problem, you will see them using an effective diameter. What is the effective diameter? The diameter, because if you use this small diameter, the area will go down. If you use this area, the area which is, measured by the diameter A. But if you use let's say this area in blue, the area will go up. So when the area go up, you multiply it by the same pressure, the force will go up. Which means, يا شباب, الخطورة هنا, the risk is here. If you said, let me use this area as approximation, you are in the risky side, not in the safe side. If you want to be in the safe side and calculate the stresses with your mobile phone, you should probably, as a rough estimation, you might even better off using B as a distance than A. Here, أنت تصير conservative. You are putting much larger area and the force will be much larger, but it will make you safe. However, calculating a smaller area is very risky. So you need to be very careful. That's why in this kind of a problem, they will give you an effective diameter. They will tell you maybe the diameter is somewhere in here. Okay? It is not B and not A. It's bigger than A, but smaller than B. Somewhere in between. Do you understand, ya shabab? You need to understand this very, very well. Okay. Now, so this problem, okay, will will give you that hint of what is the diameter that you should use as an effective, as well as this problem is given to you when with a type B joint, which doesn't have a nut over there. So it will teach you in metric, this is an example in metric, and it will teach you how to deal with this geometry. If you remember, we had two different geometry, one of it A, one B, and this is the second one. So this is a good exercise, but ultimately you will calculate KB, KM, and then you will find the factor of safety as usual. Okay, any question, ya shabab? All right. Now, what are we going to do? We're going to introduce you to fatigue loading of tension joint. So the words are very important. It is tension, no shear, no bending. It's just tension, tension. And it is fatigue. So the first thing that you should know is that as much as you might think that this is going to be a tough deal, why? Because here you have a threaded part and you have a knot and so on. So how are you going to deal with those complexities? However, whenever complexity arises for at least design practices, they come, the societies and the group, research group, they try to investigate things and then provide us as a standard values. So interestingly, when it comes to the fact that you have a thread and the thread is going to raise the stress because there is discontinuity, there is sharp edge. However, the fact is way easier than what you think. In reality, what we have an experimental evaluation of those threads, and we have some standard values. So for a grade, for example, for SAE grade 0 to 2 or 4 to 8, or the metric grade 3.6 to 5.8 or 6.6 to 10.9, you have three types of threading method, which is rolled threads, cut thread, and fillet. Now, what are these? Ya shabab, roll threading is a manufacturing method. I am pretty sure if you just say rolled threading in YouTube, you will find a lot of nice, interesting video. But it is basically putting a rod within two jaws or two faces of the machine, and they slide one against each other. And there is a surface which is threaded. And when the part rotates, it rolls, the thread is being cut. This is called roll threading. There is a cut threading. In the cut threading, you take the shaft, and then there is a hollow cutter which has a thread inside it that cuts the part, and then you rotate the shaft inside this cutter, and then it creates the thread for you. This is called cut threading. The fillet, I honestly don't know. I always maybe thought that this is when you have I need to search for it. I honestly thought that this is much more related to the fact that the thread itself is rounded, okay? But I can check it for you later. So what happened is this. KF, remember, not KT, not Q, it's KF. The fatigue stress concentration factor is given to us. So if you are having a metric thread with a class grade 3.6 to 5.8, and this is a cut thread, this is KF is 2.8. If it is rolled threading, it is 2.2. Do you understand? So this is very interesting. It just makes our life much easier than what we thought. Not only this, ya shabab, if you want the reality, there is even more interesting thing, which is the fact that the fully corrected endurance limit is actually standardized or provided. So what is this? This is the fully SE, which means it is KA, KB, KC, KD, KE, KF multiplied by SE prime. Somebody did all of this. They estimated the actual endurance limit experimentally. And these values are provided for what, ya shabab? Roll threads. Roll threads. Now, roll thread, we're going to talk about them, okay, with respect to cut thread. But here, what do you have? You have SAE grade 5, 7, 8, and this is the size range of the bolt, or ISO and metric, you know, the metric range. So, and for example, if you have M16, M metric 16 millimeter diameter, then the endurance limit is 129 megapascal. This is way easier than what we would expect if somebody talked about fatigue for a threaded part. I mean, the endurance limit is given to us, the KF is given to us, so the remaining part will be just going and finding a certain criteria, get the loads and put them in, as we will see. So what do we want to talk about here is that there is a hint here, is very important, which says that this table 817, which provide you with the endurance limit, is for rolled threading. And it is saying as per the book that for cut threads, it is anticipated that the endurance strength will be significantly lower. So with respect to us in this textbook, we have an access to this table. So we will always assume that this is a cut thread. Everything we will bring it in the homework, it's going to be cut thread. And if it rolled thread. If it is a cut thread, we will assume that the endurance limit is the same as rolled thread. And we will use KF differently for cut or. This is the best that we can do. But if you are probably working in an industry which needs this information, you will either have your own lab testing them for you, or you hire a company or a university to test them for you. Or if you are lucky, you have them tabulated in some sort of standard somewhere. Do you understand? But this is very important. Now, what I want to talk about right now is when we know SE, when we know KF, and we know that there is FI, there is CP, and so on, we will take these loads and these stresses, like the endurance limit is a stress. And then we will use Goodman and Gerber in some way to find a relation that tells us what is the fatigue strength. Or, I mean, what is the fatigue factor of safety for the joint. Now, but what I want to do is to tell you, if we come back to this example, okay? And what I want to explain to you, think that as follows. You can think that for this pipe, okay, like this, and let's assume that this is the pipe now. What do we have? We have the wall of the pipe over here and this pipe over there. So as we said, we have the fluid, okay, whether it is gas or liquid, coming up here. So my question to you, if you have a condition like this, a pipe, inside it there is a fluid, is this a static problem or fatigue? What is it يا شباب? Anyone? No one knows يا شباب. Are you here يا شباب, or I am talking to myself?
Yes, we are here.
Yes, doctor.
Yes.
Yes, doctor.
Yes.
So, what do you think? Is it a static or fatigue? Just let's make a vote. Who said it is a static? Just raise your hand.
Static of what, doctor?
Is it a static problem? Or is it a fatigue problem?
It is a fatigue problem, doctor.
Yes, Dr. Fatigue.
Okay, who would say fatigue? Please raise your hand. Oh yeah? Whoa, 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 look at these hands. Okay, how is it fatigue? Anyone want to tell me how? Fawaz, you want to talk?
نحسب الكي اف يا دكتور.
What?
نحسب الكي اف يعني. Doctor, because the load is variable.
Why it is variable?
The flow of the gas or the liquid will not be a constant.
Why not?
I am assuming that it is not continuously flowing. It may vary.
Yeah, okay, good try. Now, what happened يا شباب? What happened is this. You mean if you have this problem, you can fairly assume إنه والله أروح سابق جبير صناعية and I see all of these pipes. And at any instant of time, if you take a camera and you take a snapshot, okay? And at that snapshot, okay, يا شباب, will give you the gauge with a pressure P. So when you take a snapshot, you go home, you zoom here, and you find that P is equal to 200 kilopascal. And then you say, with full confidence, that the pressure here is 200 kilopascal. And if I take, let's just make it simple, okay, and say that the ceiling is going up to here, so I don't need to worry about effective area. I have this area. Now, this area, A equals to pi over 4 dA square. And then I multiply this by P, and I find F. And when I find F, I go and I divide it by the number of bolts. And then when I know P, I go and find NL, NP, and N0. Fair enough. That's the first check. But when you take a video, not a picture, you will realize that while you are watching the video, this pressure might change. Now, just to give you an industrial story, just get excited and تعرفون شركة يوكاغاوا يا شباب. Yokogawa company has an office here in Dhahran Techno Valley, our Dhahran Techno Valley. Now, Yokogawa is a big Japanese company, and they are famous for one thing. Many things, but one thing they are famous of, which is their control system. What is their control system doing? Yokogawa claims that when they go to Sabic or Aramco, يا شباب زي ما تعرفون, or if you talk thermodynamics too, it will teach you that when there is a mixture, air and humidity, this mixture, if you push it in a pipe, and then at certain stage, you change the pressure or you change the temperature, that mixture will start to become something different. Like what? Like water start dripping. The mixture is like humidity in the air. You don't see the water, just you feel it. But if you put some sort of mechanism to play with the pressure and the temperature, you can take that humidity out by separating the water which is saturated in the air. Now, in the pipeline, they don't want to do this. They want the mixture to go the same way. So pipes goes everywhere in the factory, and sometimes they go from one city to another. And they want to keep the same mixture in the same condition. So it's very challenging. If they don't need to control the temperature, they are lucky. But most of the time, they need to control the pressure. And believe it or not, يا شباب, in a factory, في مصنع, إنتاج طاقة, غاز, whatever, there might be thousands of valves. Do you know what are the valves, يا شباب? Have you ever heard about them?
Yes, of course.
أكيد مو زي العفريتة.
لا أكيد دكتور.
ترى ما هو شيء يوكل هو الفالف. Just to let you know. Okay, so what happened? You would think that valve in the factory يجي واحد كذا يفتح الفالف ويتركه. No, probably all of the valves that are connected to the operation, the production process, okay, are combined with actuators. Actuators are electronic device that control the valve. So literally, يا شباب, حرفيا, الvalve in the production line can open and close, like somebody is opening and closing it, like every second. A little bit, a little bit, a little bit, a little bit. Unbelievable, right? Yokogawa are probably one of the best or the most leading companies that will make thousands of valves open and close in a very controlled way. And in the end of the day, you may see this pressure gauge going a little bit up and down, but within a controlled fashion. So the process engineers, like chemical engineers, okay, they will come and tell them, listen, you need to maintain the pressure between 290 to 310 kilopascal. Now, خلاص نقول للكيميكال انجينير مع السلامة شكرا. نجي الآن حق السيستم انجينير ونقول له يلا اشتغل مع يوكوغاوا and make sure that all of these valves will open and close almost instantaneously to control the pressure. I want the pressure in every single point in the pipe. Maybe the pipe go up, down, left. Maybe it is like 10 kilometers. And I want the pressure to be maintained. يجي الميكانيكال engineer يقول we can't. We need to put a step up pump over there. And we need to put another pump over there. And we need to put... So all of these system, chemical, mechanical come together to make this one single long pipe, a very long story, right? So in reality, you will have your pressure fluctuating, maybe a little, maybe a lot, we don't know. Yes, يا محمد.
طيب دكتور، ليش ما يكون في هذا requirement في البداية ان الانترنال بريشر a given value ويصير الديزاين على اساسه بدال كل التغيير
Yes, but we all know from Bernoulli equation and others that pipes are not straight and you need to have an elbow and you need sometimes different diameters. So as the volume rate changes, the pressure change, the velocity change, you can't. Another thing, friction. The friction, do you remember that? We talked about friction and viscosity of the fluid while it moves in the pipeline, its pressure will drop because of internal friction and friction with the wall. So there is no way you can just say, okay, let me bump here 10 megapascal, and then it will go all the way to the 10 megapascal. This is just never gonna happen. That's a sweet dream, pink dream, which never gonna happen. Okay, that's why Yokogawa is a probably multi-billion company said, oh, that dream doesn't happen, I'm gonna make money out of it. That's it. That's the story. I think, if I'm not mistaken, they are famous for their system is called SCADA. I am really confused between a system which is used to control نفس الستوري حق الكهرب. أهل الكهرب عندهم نفس القصة ما بين الكرنت والفولت والباور. نفس القصة. Exactly. And that's why they put step up, step down transformers along the line and so on. ومحطات وسالفة. It's exactly the same story. إذا ماني غلطان, SCADA is the software that was developed by Yokogawa. And sometimes I may be wrong. Maybe SCADA is the one that is used by the electric company to. I really forgot. Maybe I need to check it next time. So, ya shabab, in the end, I need you to understand what are the sources of cycling here. So, one last example before we end the lecture is the power generation plant. كلنا نعرف إنه في عز الظهر في الصيف the electric demand, the electricity demand will reach the peak. Now, just imagine that everything in the power generation plant will reach the peak. The pressure, the temperature, everything. But at night, it may drop a little bit. Now, that drop little bit, it might be very little, like 1 kilonewton or something, but it is cycling. And if it is happening every day, every second, these machines will be fatigued, right? That's what fatigue is all about. So you might have crack after 10 years or something. So that's why it is very important. Next class, inshallah, now you understand how cycling is happening here. So next class, we will assume that there is cycling and we are going to deal with it. Okay, that's it, ya shabab. Let me ask you, please, to turn on your webcam. I'm going to take the attendance. And don't forget, if you made that survey, respond to it very quickly. Another thing, ya shabab, only half of the class did the evaluation. So next class, maybe I will give you some more time to do it. Okay, I don't see you, ya shabab. Where are you? Okay. Raheli, Hussein?
Yes.
Where are you? Okay. Saleh, Saeed?
Yes.
Adnan?
يس
الخضير؟
اي على الخضر اي موجود.
Where are you? Yeah, okay, I see you. Muhammad Al-Madan?
Yes, here.
Sultan?
Yes,
Sultan
Doctor.
Saleh?
Yes.
طويليب علي؟ Okay,
يس دكتور موجود.
وليد العمري؟
يس
فيصل؟
موجود دكتور.
علي؟
Yes, دكتور.
محمد؟
يس دكتور.
مفلح الدوسري؟
Yes, دكتور.
غريب؟ فهد؟
موجود.
فيصل؟
يس دكتور.
مصلح الحارثي؟
Yes, دكتور.
هوشاني سلمان؟
موجود دكتور.
فارس جبرين؟
موجود دكتور.
خالد؟
موجود دكتور موجود.
سعد؟
يس دكتور موجود.
عمر المالكي؟
موجود دكتور.
ثامر مطوع؟
يس.
مصطفى attended the other class. فواز العوفي.
يس دكتور موجود.
أمجد.
Yes, here.
فيصل.
Yes, doctor.
سويق. محمد. I thought he was here. Where are you? محمد. I think.
Yes, دكتور.
ناصر.
Yes.
عبد الرحمن.
Yes, doctor.
Yes, دكتور.
عمر.
موجود.
بديوي. محمد.
حاضر دكتور.
مؤيد.
Yes, doctor.
and محمد.
Yes, دكتور.
Okay. Yes.
محمد صويق دكتور.
Yes. I checked you. I think I have few students coming from the other section.